Another useful probability distribution is a Poisson probability density function, or waiting time distribution. This distribution is used to determine how many checkout clerks are needed to keep a waiting time in line to a special level, how many telephone lines are needed to keep a system from overloading, and many other practical applications. A modification of the Poisson, the Pascal, developed more than 4 centuries ago, is used today by telecommunications companies worldwide for load factors, satellite hookup levels, and internet capacity problems. The Poisson distribution has a discrete random variable, although it is measuring across a continuous variable, usually time or space. This distribution solves this problem by dividing time into discrete pieces. The formula for computing probabilities that are from a Poisson process is the probability of x is equal to e raised to the negative mu power times mu raised to the power x, all divided by x factorial. Where probability of x is the probability of x successes we are interested in. The Greek letter mu is the historical expected number of successes in any given time period, and e is a natural logarithm approximately equal to 2.71828. In order to use the Poisson distribution, certain assumptions must hold. These are the probability of success, mu, is unchanged within the interval. There cannot be simultaneous successes within the interval, and finally, that the probability of a success among intervals is independent, the same assumption of the binomial distribution. The Poisson distribution can be used to calculate the probability of a specific number of successes based on the historic mean number of successes. In order to apply the Poisson distribution, the various events must be independent. Keep in mind that the term success does not mean success in the traditional positive sense. It just means that the outcome in question occurred. Imagine that the historic number of telephone calls to a fire station on a weekday is 8. What is the probability that 11 calls will come in on a weekday? For example, we can fill in the terms of the formula as follows. We write the probability that x is 11 equals e raised to the negative 8th power times 8, the historic average number of calls, raised to the 11th power, all divided by 11 factorial. Remembering that e is the base of the natural logarithm, equal to 2.71828, we find the probability is 0.072, that the fire station will get 11 calls. Since the historic mean is 8, and the question asks about the probability of getting 11 calls, it turns out that it is a very unlikely situation. Another common use of the Poisson distribution is to find the probability of specific waiting times, often called queuing time problems. Assume that historically people arrive at the checkout counter at the rate of 2 every 15 minutes. If we assume these arrival times are independent, the Poisson can compute the probability of, say, more than 9 customers arriving in a 1-hour period. This might be an interesting piece of information to the manager of the store if it is known that the average time to process a customer is 10 minutes. The store now wishes to trade off the cost of unhappy customers waiting in line against the cost of added checkout clerks. This is, of course, what we see at Christmas time as more clerks are added to reduce customer frustration and thus sales. The answer to this particular problem is solved by first adjusting the information to uniform time periods. There are 4 15-minute periods in 1 hour, so the historical data is adjusted to be 8 customers per hour, from 2 per each 15-minute period. Mu equals 8. The question can be mathematically stated as the probability that the number of customers each hour exceeds 9 equals 1 minus the probability that the number of customers is less than 8 each hour. This requires us to calculate all the probabilities from 0 to 8, inclusive, and then subtract from 1. The first term would be probability of x equals 0 equals e raised to the negative 8th power, 8 raised to the 0 power, the whole thing divided by factorial 1, which is equal to 0.000335. The second term would be the probability that x equals 1 equals e raised to the negative 8, 8 raised to the first power, all divided by 1 factorial, which is equal to 0.00268, and so on. I will leave it to the interested student to reach the final solution. Hint, the answer is that the probability that there will be more than 9 customers in the next hour is equal to the probability x is greater than 9 equals 1 minus the probability x is equal to or less than 8 equals 1 minus 0.592 or 0.407.